Good afternoon. Thank you very much. Just bear with me because I've had my eyes done. Right. I'm going to talk about design and resilience of sheet pile structures for vessel impact. Examples of protection of structures with sheet piles, independent and direct protection design, damage issues, resilience of piles and their interlocks, and strengthening the walls, vulnerability situations, and detailing for robustness. It's necessary to protect permanent structures in waterways, tidal estuaries, especially where there's large vessels, high momentum, and risks of major impact and damage. So the problems facing the designer, the consequences of impact, protection limitations, minimize risk of collapse, and limit the extent of collision damage. So we look back to 1980 for the terrible Skyway Bridge disaster in Florida, where the Summit Venture was approaching the Skyway Bridge when an awful storm hit it and sent the vessel off course. There was multiple loss of life after hitting the bridge pier. The collapse caused extensive damage and long-term suffering. 35 people were killed. There was only one survivor from a vehicle falling off the bridge, which took about 400 meters of carriageway into the water. So there's lessons to be learned from this unprotected bridge foundation, which means that the designer for protection of bridge piers has to consider probabilistic modelling for the angle of impact, speed and momentum of the vessel, and how it's affected by the angle of approach. So we've seen a bit about statistical modelling, but this is also important for the design of the structure. So we'll start at looking some indirect protection of bridge piers, and this is at the top end of the scale for impact velocity from large ships. So we're looking at very heavy gravity structures using sheet piles, in this case at the Second Incheon Bridge in South Korea, 2008. And here on the left hand side you can see the straight web cells have been built on land and carried out into position by a very large crane, and then positioned in a series of protective cells around the bridge structure. So gravity wall straight web cell up to 30 to 35 meters height, built on a firm or hard seabed with a massive protective cap for the impact to tie it all together. So the details of sheet piles, and this is why it's easier to build it on land than in the water. The sheet piles themselves have a very robust interlock for a straight web pile, and they can take up to 5,500 kilonewtons per metre. You can strengthen the individual piles with strengthening plates. And section looks like this, with a very robust cap, and the concrete is, or the RC concrete is connected to the sheets by multiple shear connectors. Gravity cell is usually, the diameter is usually greater than 0.8 of the retained height, and in this case about 20 to 25 meters wide. You can check by FE analysis the impact forces and the shear stresses on individual elements due to tilting of the structure. The second one is this one in Barcelona, Spain, 24 meters high, bit more embedments, 14 meters draft, and the cells are arranged in pairs to protect the bridge foundations, with some appreciable distance between the bridge substructure and the protective gravity cells or dolphins, to allow for substantial tilting on high impact loading. So we can also design for direct impact, but usually this takes the form of rectangular cells. This is the Sundsvall Fjärdenbro, and there's a series of rectangular embedded retaining walls to form cells to protect the foundation of the bridge. So in section, the bridge superstructure is connected to the RC pile cap, which is tied into all the walls by tension ties. And the FE analysis works out the resultant forces of impact, 30 meganewton over 6 meter spans, to give resultant deflections and energy absorption facilities, with the piles embedded to fixed embedment. In this way, you can actually beef up the stiffness of the embedded retaining walls by using combination wall systems or combined wall systems to get fixity, and then calculate the analysis by rotation from fixity from the very high impact loads. So this is at the top end of the scale, and basically the details will be for robustness at the level of impact. Sheet piles will be tied and connected into the RC top slab, usually up to about 2 meters thick. And really this is to provide a monolithic structural connection to have a robust effect on a very large impact force. So the particular details for the sheet piles, it's a good technique to tie all the pairs of sheet piles, in this case Z piles, together by off-center tie details, which we can find in the brochures. And actually weld the interlocks of the sheet piles at the top, and the RC slab functions to transfer the load directly as a wailing and make the structure act monolithically at that level. So the actual details on the connections of the concrete to the sheet, it's very often in this case you will have multiple shear connectors. Here we have about 144 per pile over 2 meter thickness. So moving on to what happens to the sheet piles. This illustration shows if we do not have robust connections or wailings at the top. I think this is in the Gladstone River in USA. No, that's not the name of the river, it's at Gladstone. But this is a simple cantilever wall that's protecting a pumping station being built in the river. But something has gone wrong here. We have to be very careful with cantilever sheet pile walls to provide protection because they're very flimsy. But when we have soft alluvial soils that show quite stiff in the bore log report, just the action of a dynamic force or impact that can easily loosen. And in this case, it collapsed on on higher flow and removal of passive resistance at the toe. So that's just an illustration of sheets collapsing. They actually stay connected together because for these sort of structures you should be looking at hot rolled interlocks to 10248. These have been tried and tested over 80 to 100 years and are well proven to take high load. So in the testing we normally do pull-out tests. This is an ongoing part of quality control, but by simply welding either side of the interlock you can reduce the stresses significantly. So it's a good technique to weld the top of the piles in the impact area. This is a typical test rig. This case we test the intermediate piles for use in combi walls under very high pressure and load. So we're talking about testing the sheet pile itself to deform before interlock, pull out or splitting. So we can use this in the design of our walls, especially in combi walls, by using the lighter range of the Zs under loads of 30 to 50 MPa. You can get some flexibility, allowing some energy absorption before rupture or splitting of the interlock itself. So one of the best ways to strengthen walls for resilience is by using combi wall type design. In this case we have tubes. So tubes can increase stiffness up to an EI of for 1 to 1.4 meter diameter tube. You can have EI bumping up to something like 1 to 2 million kilonewton meters squared per meter. The maximum stiffness you can possibly get for a sheet pile is about an EI of 250 kilonewton meters squared per meter. So we can increase the stiffness of the wall by up to 10 times by introducing combi piles. This is important for the rectangular type of structure for energy absorption, because you'll have the whole structure rotating about the point of fixity. So you don't need the intermediate piles at the toe. You can actually protect the intermediate sheet pile by reversing it for a design for a structure for impact from vessels. So normally we'd put the Z pile this way in a combi wall, but there's no reason why it can't be positioned that way. You can always protect the tube by filling it with concrete. So this is a study similarly testing under pressure to see the movement in a combi wall. In this case we've got the 8Z type combi wall with a comparison of performance on deformation between a pair of Zs, a pair of Us, and a triple U. So by allowing distortion and movement of the intermediate piles, we can, without declutching and losing fill, we can study the resilience of the structure. So, I think I've missed a slide out there. Anyway, the Z pile slide has gone, the HZ. So this is an example of strengthening a normal sheet pile wall with HZ combination primary piles, so in this case at the corner elements. So at any point along the wall we can introduce HZ combi primaries to strengthen up the wall. And similarly, you can also connect the Z piles at the back flange. So you can have a face of a key with very strong primary elements up to an EI of 1,000,000 kilonewton meter squared per meter, and protect the Z piles by installing them on the back face. Now look at the vulnerable part of the structure construction, that is cofferdams when we're dewatering. So it's quite important this to protect the vulnerable face. So either the normal way is to have temporary dolphins or channel barriers, but the lower we get in the cofferdam and the dewater stage, there is increased risk. So it's best in the temporary phase to have a very a warning system or a lookout or some means of making sure that there's no impact in this very vulnerable stage of the construction of the cofferdam. Flooding and reverse technique to make sure that the base is constructed safely before there's any risk of anything going wrong, especially by having something hit the outside face. So I think this structure in one of the tidal rivers in Wales was round about late 90s. So this is a circular cofferdam under dewatered phase. So if you note, these wailings look rather modest, and would never recommend this. It's always best to have very robust elements in temporary structures. And in this case, this was quite vulnerable. There's always a danger of failure at support frame level, but if it were subject to impact, the sort of thing you're about to see could easily happen before you construct the permanent base or the foundation. And this happened in a matter of seconds. So a base failure is a catastrophic situation, and luckily nobody was killed because everybody had gone off to lunch when this happened. It's certainly a lesson to be learned, and when a vessel hits a temporary structure, it can easily disturb the formation at the base level, and in soft soils exacerbated by water pressure and piping, you can lose the whole base. It'll pop out through the bottom and the structure collapses. So it's something certainly to be wary of for designing structures against vessel impact. One of the best ways to protect a structure using modern installation techniques is, in my opinion, using a double wall type combi wall structure. So instead of having the intermediate piles joining primary pile tubes together, you install a sheet pile wall first to so many meters below formation level, and then you have a very deep primary pile, in this case a tube, sitting at spacings usually can go up to 3 times the diameter. So you generate enough passive resistance with the tube below the sheet pile, but for impact protection you can use the secondary sheet or the sheet pile to take the collision forces. And you can position the sheet or the tube either way round. You can fill the tubes with concrete and put them in front, or you simply have to tie the sheets at the top. This is taken with compliments to Geeken, because this is a combined wall system that's very strong and can be installed silent and vibration free. So on the Thames this will be particularly important, or waterways where you have structures and properties right up to the edge of your new build.
Graham, just 1 more minute, please.
Yeah.
We're just running a bit out of time.
Yeah, this is the last slide.
Apologies.
So, thank you very much. I just had an illustration here of tiebacks to the 8 sets, where the tiebacks are protected by connecting onto the back flange, and you increase robustness by protecting the top and being able to dewater and connect on the inside rear flange of the 8Z. In this way, the whole process of construction inside the cofferdam can be maintained in a robust fashion as possible. So thank you very much.